In this video, I'll be going over compound interest. And so let's go ahead and get started. It says here in financial formulas, the principal is the starting amount that is borrowed or invested. In our discussion on simple interest, we called this the present value, or at least that's another name for it. Now, simple interest is interest paid on the original principal only. Compound interest is interest on the principal and any accumulated interest. So I'll give you an example. So there's a good chance if you have a checking account and you also have a savings account that you're getting compound interest on your savings account. So let's say you have $100 in there. At the end of actually, it's usually compounded quarterly. In some cases, it might be monthly. So let's say it's monthly. So at the end of the month, you would get, let's say the interest rate is 2%. You would get 1 month's interest at 2% on that $100. And so the next month, you would be earning interest on the original $100 that you put in there, plus the interest that you earned in the first month. So that's the basic idea. In fact, anytime you're earning interest on interest, that's when you're receiving compound interest. All right, so let's look at how this works. So simple interest versus compound interest, I'm right here. It says Jason borrowed $2,000 from his Uncle Vito for 3 years at a simple interest rate of 10%. How much interest will he pay for borrowing the money? Now, we learned how to find simple interest. We use this formula, I equals PRT. And so if you plug in the principal, the interest rate written as a decimal, and the time, you get $600. So to borrow this money for 3 years, it's going to cost Jason $600. Uncle Vito's making a little money off of his little nephew there. So let's look at A here. It says if he intends to pay his uncle back in full 3 years from now, what will he owe his uncle at that time? Well, he's going to have to pay the $600 in interest plus the $2,000 that he owes him, and so that's going to be $2,600. Now, you may recall we have a formula for this. It's actually called the future value formula when we're working with simple interest. So it's this one here. And so if you plug in, remember A stands for the future value, and again P is the present value, which in this case is $2,000. So let's plug in our numbers, and when you multiply this out, you also get $2,600. And I'm just showing you this as an alternate way you can find the same answer. All right, in B it says if Jason had to pay 10% interest compounded annually, that's every year, how much interest would he pay for borrowing the money? And then what balance would he owe his uncle in 3 years? So let's look at this. So in year 1, the interest is going to be 10% of $2,000, which is $200. So since the interest is compounded each year, what that means is that $200 is applied to the balance of the loan. And so in year 2, Jason's going to have to pay 10% of $2,200, the $2,000 that he originally borrowed, plus the interest from the first year. And so the interest that'll have to be paid at the end of year 2, or I should say it'll be applied to the account after year 2, is $220. And so now that's going to be added to the $2,200 that he already owes. And so in year 3, Jason's going to pay 10% of $2,420. That's the $2,200 plus the $220 in interest from that second year. And so finally, in the third year, he's going to pay $242 in interest. And so if you add all that up, he's paying $662 in interest. So that's an extra $62 because the interest was applied to his account or his balance each year. Now, it also says what would he owe his uncle in 3 years? Well, again, he's going to have to pay the $2,000 he borrowed plus the $662 in interest, and so that's $2,662. And with a name like Uncle Vito, I would not be late. Let's move on to the next slide. All right, so here it says compound interest formula for interest compounded once a year. Now, the problem we just did, what if the loan was for 20 years? I mean, would you want to have to do line by line what we just did? Well, there's a formula for that. We don't have to do that. And this is the formula. Notice it says A equals P times the quantity 1 plus R to the T power, where A is future value, P is the principal, R is our interest rate, and T is the number of years. So if we actually use this formula for the last problem, and you plug in the numbers, so 2,000 is the amount of the loan, times 1 plus R, which we'll write as 0.10, that's our 10%. The time was 3 years, and you'll see we get the same number that we got on the preceding slide. All right, I would encourage you to go ahead and try number 1 here. It's just a matter of writing the formula and then plugging the numbers in, and then you've just got to make sure you can get the answer correct on your calculator. All right, so here's our formula. Our principal is $12,000. It'll be 1 plus 0.02 since our interest rate is 2%, and the time is 5. That'll be our exponent. And you should get $13,248.97. Now I want you to notice something here. Let's say you were trying to save a little bit of money. You have $12,000 saved for a car, or who knows, that's money you have in savings, and you want to wait another 5 years and then buy a car. Well, you can see you only earned $1,248.97 in those 5 years. You can see when your interest rate is low, here it's 2%, your value is not increasing very fast. So that's why people are always looking for a better interest rate. But of course you've got to be careful, because the higher the interest rate in general on an investment, the more risk you're going to be taking. And you don't want to lose that money if you're planning to use it to buy a car. All right, so let's go ahead and move on to the next slide. So now, that was for interest compounded once a year. What if it's compounded more frequently? So we'll look at an example here. Consider how quarterly compounding affects a $1,000 investment at 5% per year. So if you look at the first line here, in the first quarter, or after 3 months, the interest paid is going to be 1,000 times 0.05, that's our interest rate, times the time. Well, since it's a fourth of a year, the time is only 0.25, which is 1/4. And so you're getting $1,250 in interest, and so the new balance is $1,012.50. And so you can see how every 3 months we're going to be getting paid interest on our balance. And so we are earning interest on interest, but this is compounded more frequently. It's every 3 months or every quarter. All right, so so I'm going to go ahead and write down the formula, and I'm going to use it for this problem here. So in this problem, the starting amount or principal is $1,000 times 1 plus 0.05, that would be our interest rate written as a decimal, over n. Now n is the number of times that the money is compounded per year, or basically how many times they're applying interest to your account per year. So if it's quarterly, we're going to say every 4 times a year, which is every 3 months. So in this problem, n is 4, and that'll be to the nt power, which is 4 times 1, because this at the end here we're after 1 year, and you get $1,050.95. Now you'll notice the numbers it's 2 cents difference. As I did the work here, I did some rounding, and so that's due to a rounding error. All right, so let's go ahead and, I mean, you can see what all the variables are here, but really the only thing that's new is the n. And again, that's just how many times they're applying interest to your account each year. And before I go on to example 2, we said for quarterly compounding, n is 4. There's a few other cases that you'll run into. If the interest is compounded semi-annually, then n is going to be 2. That means twice a year, or every 6 months, they're going to apply interest to your account. If it's monthly, then n is 12. And if it's compounded daily, then n is going to be 360. So notice we use 360 for daily. All right, so let's go ahead and look at example 2. It says, Grandma and Grandpa want to put some money away for college for their brand new grandchild. They deposited $20,000 in a bank account that pays 3% interest compounded monthly over 18 years. Well, that's when she'll be ready to go to college. How much will be in the account when their grandchild turns 18? Compare this amount to the amount that would be in the account if the interest were compounded annually. All right, so here the interest is compounded monthly. So notice n is going to be 12, because 12 times a year the interest will be applied to the account. So let's go ahead and get started. I'll write down the formula. P, or our starting amount, is $20,000, and it'll be 1 plus the interest rate, which is 0.03, divided by n, which we said is 12 here, to the nt power. That would be 12 times 18, since it's going to be 18 years before she goes to college. So if you plug this into your calculator, you should get $34,297.02. Now this is for interest being compounded monthly. I asked you to compare that to when it's compounded annually. So that's the formula that we did previously. And so let's go ahead and plug in the numbers here. It'll be 20,000 times the quantity, 1 plus 0.03, to the t power. T here is 18. And so you get $34,048.66. So I actually subtracted it, and you find that the difference is about $248.36. Now that's really not a big deal when you're talking about 18 years. I'm going to make $248 more by compounding it, the interest that is, monthly. However, I mean, wouldn't you want the greater amount of money for your granddaughter? All right, so I don't know about you, but I'm thinking, man, that's at 3%. What if I could get a higher percent? What if I could get 8%? So if you plug in 8, you actually find it's $84,011.48. The interest rate that you get when you invest your money is so important. You can see it makes a huge difference. On the other hand, don't forget, if you're looking for a higher interest rate, along with that could come some risk. Maybe the money is getting put into some kind of package of stocks and bonds. Well, there's some risk in doing that. Whereas if you put your money in the bank, you're guaranteed to get that interest rate. All right, so let's move on to the next slide. It says a sum of $10,000 is invested at an annual rate of 8% compounded quarterly. Find the balance in the account after 5 years. So I would encourage you to go ahead and do this one. It's just another example of what we just did, and then watch the video and check your work. All right, so there's your formula. You got your P here, your starting amount is $10,000. It'll be 1 plus the interest rate, which is 0.08 when you write it as a decimal. And compounded quarterly, we're going to use 4. And then it'll be 4 times 5, n times t, since it's 5 years, and n is still 4. And when you plug that in your calculator, you should get $14,859.47. So you're making almost $5,000 in interest in those 5 years. That's not bad. So an interest rate of 8 is nice, but it's be very difficult to get that kind of interest rate right now without taking a little bit more risk. All right, so let's look at the next problem here. It's in Roman numeral 5. It says planning for the future with compound interest. So it says if A dollars are to be accumulated in T years in an account that pays rate R compounded N times per year, then the present value P that needs to be invested now is given by this formula here, A over the quantity 1 plus R over N to the NT power. Now, I hope that you recognize that what you're really seeing is this formula here that's been solved for P. And so we're going in reverse. We're saying, hey, and actually I'm going to go ahead and make a comment here. This formula is used for savings goals. In other words, I'm not saying like in problem 2, I said, all right, I'm going to invest $10,000 for 5 years. How much will I have in 5 years? Now I'm saying, hey, I need to save this amount, or I want to save this amount. How much do I need to invest right now? What does my P need to be in order for me to have that amount in T years? All right, so let's look at an example. In example 3 here, it says Michael wants to save for a car. How much money should he deposit in an account that earns 6% interest, compounded semi-annually, so that it will accumulate to $25,000 in 5 years? So you might just take a guess at how long or how much money you might have to invest. Now let's go ahead and figure out what this number would be. So in 5 years, he wants to have $25,000 to spend on a car. All right, so here's our formula. In this problem, A, the amount we want to accumulate, or this is our future value, we want it to be $25,000, and we want to divide by 1 plus R, which in this case is 0.06, divided by N. Notice that it's compounded semi-annually, and so that would be 2, N would be 2, and that's to the NT power, which would be 2 times 5, since it's 5 years. And when you plug that into your calculator, you should get $18,602.35. So in 5 years, you're making some pretty good interest. That would be nice. Now, here's the problem. How many of you have $18,600 and some to just throw into a banking account for 5 years? Most people are not able to do that. And so what they do is they take money away each month from their paycheck or whenever they get paid, and they save a certain amount. And so that's what you would need to know. How much do you save each month so that you'll have that $25,000 in 5 years? And that's what we'll talk about in the next section. Let's go ahead and finish out this section. On number 3, it says how much money should be deposited in an account that earns 4% interest compounded daily so that it will accumulate to $15,000 in 8 years. Well, what I would encourage you to do is go ahead and do this problem. It's just like the last one, and then check your work. So here's our formula. When you plug in the numbers, it'll be 15,000 over the quantity 1 plus 0.04, since our interest rate is 4%. Notice it's compounded daily, so here N is 360. And then it'll be NT, that'll be 360 times our time, which is 8. And you should have gotten $10,892.43. That's how much you need to invest now so that in 8 years you'll have $15,000 under these situation. I should say, given these details, the interest rate and the time. All right, let's move on to the next page. And the last thing I want to talk about is the effective annual yield. Now, the effective annual yield is the simple interest rate that produces the same amount of money in an account at the end of 1 year as when the account is subject to compound interest at a stated rate. What are we saying here? Well, if interest rates, are sometimes compounded quarterly or monthly or annually, how do you compare so that you can choose the one that's going to make you the most money? Well, the effective annual yield is basically telling you what you would actually earn in a year in terms of simple interest on that investment. And so it evens everything out. The other way that we describe this is annual percentage rate, or APR. So I do want to mention that when you use this formula, you want to make sure that you change your decimal to a percent. So it says, suppose that an investment has a nominal interest rate R in decimal form and pays compound interest N times a year. The investment's effective annual yield Y in decimal form is given by, and it's Y equals the quantity 1 plus R over N, all to the N power minus 1. So an example for it says, what is the effective annual yield of an account paying 8% compounded quarterly? Round to the nearest tenth of a percent. So let's go ahead and write out the formula, and let's plug in the numbers. So in this problem, R is going to be 0.08. So it's 1 plus 0.08 over N, which they said was compounded quarterly, so N is 12. I'm sorry, quarterly, N is 4. And that would be to the 4th power minus 1. And so you get 0.0824. Remember, we want to write that as a percent. So that's 8.2%. But it does say that they want you to round to a tenth of a percent. So basically stop right there. So since that's a 4 that comes next, we'll leave that 0.2 alone. And so our answer is 8.2%. All right, so we have one last problem here. And I would encourage you to do it and then check your work. So in this problem, we'll use the same formula. We're going to plug in R, which will be 0.06. Our N, since it's compounded monthly, N will be 12 to the 12th power minus 1. And you should get 0.06168. I don't remember if it goes beyond that, but that's enough decimal places, which is about 6.168%. But again, we're going to stop at the nearest tenth of a percent, and so that would be 6.2%. And that's it for this video.